Alright, so yeah, welcome back to week 2 of the computer vision reading group. This week we'll be talking about image segmentation. Just a quick recap from last week. We talked about image detection and recognition, and image segmentation is actually, I think, a stronger form of image detection. So we get more familiar with the techniques, what type of models are there, and what type of tasks we could do for that. Just to give you a quick rundown of what exactly image segmentation is, what you're trying to do is quite simple. Actually, you're just trying to partition an image into multiple segments. And what I mean by that is, we're just trying to assign each pixel in the image to a class, right? So now that rather than detecting these bounding boxes of these objects that we might be interested in, we're going to label every single pixel corresponding to a class, right? So it's pretty straightforward in that sense. This picture does a pretty good job just showing you the difference between classification and localization, which is what we talked about last week, and also semantic segmentation, right? Yeah, and there is that. So just to give you a little, idea of where exactly segmentation lies on the spectrum, I'd say, in the most simple form, we have image classification, right? Which is on the left-hand side right here. It just recognizes what type of objects are inside the image. Too bad it's not very useful in many cases. A stronger form of that would be detection, right? So not only are you just detecting, classifying what type of objects are inside the image, you're also locating where exactly they are by drawing these bounding boxes, right? And so last week we talked about these methods like region, CNNs. Yeah, they all achieve this type of goal. And this week we're going to be moving into segmentation and instance segmentation. Image segmentation in its broadest form, you're just assigning, like I said, you're assigning each pixel in the image to a class, right? So given this image on the left-hand side, I think someone's asked you to join. Oh, nope. Yeah, so, with this image, you're basically, yeah, like I said, assigning each pixel a membership, right? And then you have an even finer form of this, which is called instance segmentation, right? So like in computer programming, OOP, oftentimes what we have is we use classes, right? And image segmentation basically just segments objects based on the class. However, what you might do is you might instantiate a bunch of objects of these classes, right? So this is called an instance of the class. And so, there might be multiple cubes in the image. So we're gonna segment them independently of every other cube, right? And so that's exactly what instance segmentation is. It's actually, yeah, it's even finer form of image segmentation, right? And so far last week, we saw all these CNNs. What the overall structure of these CNNs is, you first have some convolutional layers to extract some meaningful latent features, right? And then we pass that into, let's say, maybe a feed-forward neural network or an SVM for classification. The thing about these methods is that it kind of just bins each image into a discrete class, right? And now the question is, can we use this architecture to sort of label each pixel in the image as a class now? That's not very easy to do. One naive approach might just be to, the number of units, output units you might have are just the total number of pixels in the image. And then basically what you do is for each output node that corresponds to a pixel, you just output what class it is. However, that's quite naive and it turns out it doesn't work so well. And so an answer to this question, can we use this structure? The answer is we cannot, right? So what do we do in this case? The solution is actually quite easy, quite straightforward. You just replace those linear layers or nonlinear layers with convolutional layers, right? And so what we call this type of model a fully convolutional neural network. And you'll see why this is valuable later on. Before we get into that, just recall that previously, we kind of have to reduce the dimensions of the features before passing it into this feed-forward neural network, for example, right? And we do the exact same thing with fully convolutional neural networks, and that's very important because you're able to capture more semantic information inside the image. But you have to be able to recover the original dimensions of the image so that you could classify each pixel of the image, right? And now, if your dimensions are very small after your first set of convolutional layers, you're gonna have to recover it by doing what's called upsampling, right? And there's quite a few techniques to upsample an image. In its most basic form, we could think of interpolation, right? So between any two pixels, the pixel value of any pixels between those pixels is just like maybe a cubic function, or it might be a linear function in that case, right? And so here are two examples. Spline interpolation, you're fitting like a polynomial of a certain number of order, and then yeah, on the right you have a bilinear interpolation, right? And so if you go to the sketch pad, what I mean by this is if you have a 2x2 image on this right hand side or left hand side, say you upsample it by 2, right? So now the dimension is 4x4. What you're gonna have are a bunch of these new pixels without any values, right? And so our question now is, how do we fill in these pixel values, right? And a simple form might just to be fitting a linear function, but the pixel value here would just be a linear combination of A and C, and so on and so forth, right? And so that in that case, it would just be we're fitting a linear spline to the image. And so there's a few other techniques, right? Rather than fitting, interpolation, you could just do something a lot more straightforward. There's a few methods. The first one is nearest neighbor, right? So, taking that exact same example we pretty much just saw, we have a 2x2 image with 1, 2, 3, 4. Once you upsample it to 4x4, you're gonna have a bunch of these missing values, I'd say. And so basically what you do is you just find the nearest pixel that has a value computed already, right? And you assign that pixel that value. So if we go back to the example that we just had right here, right? The nearest pixel for this pixel right here would be A, right? Because A is filled in. Same thing for here and here, right? And then you could do the same thing for the remaining, you can fill in the remaining pixels correspondingly, right? And so that is the nearest neighbor techniques. You also have a different technique called bed of nails. It's not really used too much. Basically, you just fill in all of the missing values with zeros. It's called bed of nails because the pixel values that do have a value, right? It kind of just stands out. And so there's another technique called math unpooling. Basically, what you do is while you're math pooling, right? You keep track of which position you took the mats from, right? So they're colored here. You got blue corresponding to 5 position. The purple position corresponds to 6, right? And then while you're doing the unpooling, basically what you do is you just fill in, fill in the corresponding location with the pixel value that you have. The problem with this approach obviously is you need extra memory because you have to store the location as well. So it's not used too much, I'd say. Another technique is transposed convolutions. Some might refer to this as deconvolutions. We saw three convolutions last week. In its most basic form, it's like a 3x3 convolution, right? And that basically reduces the dimension of the image if you have like a stride greater than 1. You should do exactly the same thing, right? But other way around. So now you define a kernel that basically maps from a 2x2 to a 4x4, right? And so your kernel will still be 3x3, but basically what you do is, so say the pink value, right? You're gonna multiply every single value in your kernel by the pink value, and then you assign it to this 4x4 grid, right? And basically any overlap that you may have, you just sum up the values. So that's what transposed convolutions are, and this gives you a more intuitive image of what exactly it does, right? The blue feature map on the bottom, it's 4x4, and that's basically the feature map that we have before we apply the transposed convolution, right? And then we're basically filling in, upsampling this image to a 6x6 now by using these transposed convolutions. And it turns out this works quite well just because it gives you some extra learnable parameters that you might have, right? However, sometimes in many cases, just using an interpolation method does the trick, right? And so, transposed convolutions, it might be a little more overkill because that's additional matrix multiplications you'll have to do. Now, before we go further into the type of models we'll see today, we have to introduce this new type of convolution that we haven't talked about. So previously, what we had was a 3x3 or a 5x5, right, kernel. And the thing was each element in the kernel was sort of adjacent with each other, right? Turns out what you could do is you could increase the spacing between the elements of the kernel, right? And so, you might have a gap between all of the elements in the kernel. and then you might increase it even more, and you might have like a gap of like maybe 4, right? And the reason why this is good, especially in image segmentation, is because when you're pooling, you get a larger field of view, right? So you're able to capture more of the semantic information of the image. However, what that means is the feature map size shrinks considerably, right? Which is not good for pixel labeling in semantic segmentation, because you want to be very precise. Right? You're saying, oh, this pixel in the original image corresponds to this class, right? But if your feature maps are very small, it might not be able to capture that very detailed information. The good thing about Atrous convolutions, some people might also refer to this as dilated convolutions, is that it gives you a larger field of view, right? So it kind of does exactly the same thing as pooling. You're able to see more of the image. However, the good thing about this is it won't shrink the image considerably, and this gives you a precise, image of what exactly I mean by that, right? If you just use normal convolutions with a certain stride, right, 4, 8, 16, so on and so forth, basically what you have is the feature map shrinks considerably compared to the original image dimensions, right? Which is not good for image segmentation. However, if you use Atrous convolutions, you are able to see the same field of view, right? Almost the same field of view. However, these feature maps the dimensions don't really change considerably compared to the original image, right? Which is very good and exactly what we want. And we'll see how this is used later on. But yeah, so now I guess it's time to first introduce our first image segmentation network that we have. And it's called a UNet, right? It's used a lot in medical image segmentation, right? So on MRI images and CT scans. Basically, how you can think of this is you have an encoder, right, on the left side, and then you have a decoder on the right side. So the encoder is pretty much exactly what we saw the previous week, right? This might be a ResNet, DenseNet, whatever. And what we did last week was, after we got to the bottom, we just fed the features through like maybe a feed for a neural network, right? However, now we don't want to do that. Instead, we're gonna upsample all of these images using all of these features using the techniques we just mentioned, right? And then go back into the dimensions of the original image so that we can label each pixel, right? And the reason why you want to have this structure is because the lower levels, right, closer to the bottom, it should capture more of the semantic information of the image, while the higher levels with these larger feature maps, it captures more of the detailed, precision of like the class labels and such, right? And we also have skip connections between feature maps of similar resolution between the encoder and decoder. The idea is because basically you don't want to waste these feature maps that might be valuable for later on computation down the road, right? Yeah, and so that's UNet. Now we're going to be talking about DeepLab. Like I said, UNet it's predominantly used in biomedical image segmentation, or at least that was like how it was introduced. A lot of people use it for many different applications now. For example, satellite, street view, segmentation. Now we're going to be talking about another method that a lot of people use in other instances, such as street view segmentation, and a lot of real world data sets, right? And so that's where DeepLab comes in. It was introduced by Google quite a few years ago. Basically, what you do is you just use a CNN that has a lot of Atrous convolutions, right? So it's precisely pretty much like this model you have at the bottom right here, right? And then what you have at the end are a bunch of these logits. We can think of this as some score map, right? We might interpolate it back to the original dimensions, because after passing it through all these Atrous convolutions, even though the dimensions won't change considerably, they still do change nevertheless, right? So you're gonna have to upsample it to the original image so that you can label each pixel. And so in the DeepLab paper, they used bilinear interpolation. And then what they did is they used this thing called conditional random field, right? And it's quite complex. It's more classical computer vision, I'd say. Basically, what conditional random fields do is they just kind of refine, the scores a bit, right? So the edges are a little more detailed and exact, right? And then after you have this fully connected conditional random field, you get the final output, the final segmentations, right? And in this case, it's segmenting the airplanes, The issue that you might have with conditional random fields is it's actually quite computationally expensive. I've tried it once by appending it, at the end of a unit. It does increase the computation complexity of your model quite a bit. And yeah, so here are some other images to show you how the conditional random field works, right? And so, you have your image and the corresponding ground truth segmentation. So this is the ground truth is the mask you want to output, right? So the deep CNN that uses the Atrous convolutions, it's able to output this score map, right? So these red regions have a higher value, right? And so, after these iterations, it kind of refines the boundaries you can see, right? And so it becomes a lot more precise, I'd say, compared to the ground truth image you have. All right, and here's some more results that you have on some various data sets. The data set that they're using here is actually Pascal VOC 2012. It's quite a popular data set back in the day. And yeah, they basically really argue the fact that by using a conditional random field, it helps improve the precision of these segmentations considerably. And if if there's very fine features in the image, say like the sheep and their legs, you can see that the conditional random field is able to separate the legs a bit better compared to if you don't use it. All right. However, there's a shortcoming of using DeepLab, and the shortcoming is they use the Fitts dilation factor. So that means you can't really segment objects of different scales, right? So the good thing about this data set is that a lot of the objects, it's very centered in the image, and so they're probably of similar scale in that case. However, if you have, say like a person right by the camera, and then you have something far, far away in the backdrop that you also want to segment, then it might not do as well because the Atrous convolution might just skip that information, right? And so that's where DeepLab v2 comes in. It was actually suggested in the same exact paper as DeepLab, the first version of it. Basically what they do is they introduce this thing called an Atrous spatial pyramid pooling, right? So they basically have a bunch of convolutional Atrous convolutions of different rates, right? Different dilation factors. And for each of these convolution kernels, they just kind of pass it through, convolve across the feature map, right? And then you get some sort of features outside of that, right? And then you basically pass a bunch of convolutional feature maps. You basically pass a bunch of different dilated convolution kernels, right? Through the same feature map, right? So each output feature map should capture information of a different scale, right? And you sort of just stack them on top of each other to get the sort of pyramid, right? And so that's what DeepLab v2 does, and it's able to improve, it's able to fix the problem with segmentation of different scales, right? Because now you have a bunch of different convolutions that considers different scales of the image, which is quite good. And then, DeepLab v3 came along like shortly after, right? And the main goal is you want to create sharper object boundaries. Previously, what people did was, they used conditional random fields. However, that's more of a Fitts procedure. And so it also increases the complexity of your algorithm by quite a bit, right? The question is, how are we able to create sharper object boundaries? Well, we could draw some inspiration from UNet, right? What UNet had was they had an encoder-decoder method, right? If you take a look at DeepLab, they just pass it through a bunch of these Atrous convolutions, right? And then they apply an interpolation to get the image back into the input dimensions, right? However, that might not be very good if your model becomes very deep, right? Because then the dimensions would shrink considerably, right? And so that's why we want to use some encoder-decoder methods. Basically, what the encoder does is it gradually reduces the feature maps to capture more semantic information, right? And what I mean by this is now, the feature maps would capture entire image details. For example, what objects are in the image, where are they located, what are they doing, right? While the decoder, it gradually recovers the fine spatial information, right? So it captures the pixel-wise details. What I mean by that is actually what class to label each pixel, right? And so it's pretty much exactly what we saw in the UNet, right? Get some semantic features at the bottom while also use that semantic feature to help direct segmentation, detailed segmentation of the pixels later on. right? And so how did DFLAB v3 do that? Well, they also introduced something else, right? I'm not going to go too much into it. They also proposed a new way of applying these convolutional filters. They call it depthwise separable convolutions, and what they do is basically just a 3x3 depthwise convolution followed by a 1 by 1 pointwise convolution to kind of combine all the feature maps together. And turns out that actually improves the accuracy of it. But that's not too important. That's just more for computational efficiency. Right? And so then DFLAB v3 plus came along later down the line. What they did a few things. Originally, in the DFLAB, in the previous DFLABs, they used, for the encoder, they used the ResNet 101. But now in DFLAB v3 plus, they replaced it with another model that is probably more powerful. They call it the aligned exception. And basically, the aligned exception, the main difference is they replace the max pooling with depthwise separable convolutions, right? So it also gives you a lot more parameters to work with. So that probably also leads to the improvements in terms of like performance later on. And what they also do is for the decoder, instead of just upsampling the image, by however much, right? So like the encoder might downsample the image by 16 times, right? Previously, what the DFLABs did is they would just upsample the image by 16 times and then sort of get the prediction from there, right? But that's not very good because it might not be able to capture very detailed, might not be able to capture the details, right? So instead of upsampling directly by 16 times, what we might do is we might upsample the combined features by 4 times, right? Combine it with some other low-level features, apply some more convolutions in between, right? And then upsample again by another 4 times, right? So then we end up recovering the original dimensions that way. And the reason why this is good is because there's a lot more intermediate multi-resolution kernels, right? And so to give you some intuition, if you look at the unit again, previously what might have been done is using these very fine features down here at the bottom, they would just upsample it to hopefully recover some segmentation mask. But instead, what we do now is we upsample it slowly, right? Apply more kernels, convolutions in between, right? So that should be able to do more filtering, and then we slowly recover the image again, right? And so that's the idea of DFLAB v3 plus. Yeah, and so I guess to just give you a summary of what we talked about, there are mainly 2 types of segmentation models that you'll probably see. The first one is the encoder-decoder methods. The predominant one right now is UNets. People are making like variants of UNets left and right. Right, and then the other method is this DFLAB family of methods where they introduce these Atrous convolutions, right? And that's pretty good for tasks in real world street view images, for example, where there are lots of objects of different different scales, which is quite good. And the reason why UNets are used a lot in medical image segmentation is because there's at least where you're segmenting in like a CT scan, for example, the objects are not of too different scale, right? However, that's not the case in these real world images of like the street or something like that. Now the question is, how do we evaluate a model? It's not so intuitive because previously we just measure the accuracy, right? If our model predicts the right class, then we say, okay, that then we improve the accuracy by a bit, right? However, that's not the case for image segmentation. There's 2 things you could do, right? You could calculate the mean average precision, right? And so basically what you do is you calculate the average precision of each of the K classes, right? And then you just average them out across all the classes, right? And then you have mean IOU. This is used quite a bit. Basically, you're just measuring overlap now. IOU quite literally just stands for intersection over union, right? So you might have a prediction. So let's say this red box is your predicted segmentation mask, right? And the green box is the ground truth segmentation mask that you're trying to hopefully recover, right? Basically, IOU just measures how much overlap there is, right? And so the formula is quite literally, if you have 2 sets A and B, you take the intersection between A and B, right? So the number of pixels that are in the intersection of A and B, and then you divide it by the union between A and B, right? And the idea is if they completely overlap, then you should have an IOU of 1. While if they don't overlap at all, your IOU should be 0, right? Because there's no intersection between your prediction and the ground truth in that case. Now, the question is, how do we get a class label? It's a little more nuanced, right? And so I feel like they don't teach this enough in a lot of like tutorials. Basically, what you do is you run the image through a segmentation model, right? And say you only have like 3 classes in the image, right? So you might have the desk, the chair, and then anything else is a background. We consider it part of the background class, right? And so you're going to have an output feature map that has 3 channels, right? Each channel corresponds to the logits or the values of a certain class, right? And so these are real valued matrices, right? So the values inside the entries are unbounded, and we just call these logits. What you do after is you apply a channel-wise softmax. What I mean by channel-wise softmax is for each pixel position, right? So we call it ij. In this case, between the red pixel, the blue pixel, and the yellow pixel, you're going to impute a softmax function, right? And so the softmax function, the formula is shown above right here if you're not familiar with it. Basically what this does is it turns any sort of unbounded values into a probability distribution, right? Which is exactly what you want. And then afterwards, what you do is for the ijth pixel, we assign it to the class that has the highest probability, right? So this is exactly the same thing as just taking the argmax across all the channels. And that's sort of how you get the final segmentation mask from the output of the segmentation model, right? So you're not just getting your segmentation model to output a number, a discrete number for every single pixel. You're going to be outputting some real valued feature maps, and then you apply softmax and then take an argmax at the end of it. And then what type of loss do you use? You just use cross entropy loss. That's a very common one, right? You use cross entropy loss across all of the pixels. And then another one that's quite common, especially in medical image segmentation, is this thing called a dice loss. A dice loss is basically just another construction of intersection over union, right? It's exactly what you have here, right? So it's 2 times the intersection between your predicted and ground truth over the predicted plus the ground truth, right? And so the idea is if your dice coefficient is 1, your prediction is exactly the same as the ground truth. While if it's 0, then you're very far off. And so this is very good to use a dice loss a lot of the times because how you evaluate your models in medical image segmentation is use this thing called a dice score coefficient, right? And so why not just directly optimize that score function, right? Turns out that if you just optimize a dice loss from the beginning where your model knows absolutely nothing, it's not very stable in training, right? The cross entropy loss is actually very stable. However, it's not. It kind of implicitly learns these intersection information, but the dice loss kind of explicitly forces that, right? And so what people might do is they might have a combination of cross entropy and then dice loss, right? So during the earlier epochs, they use only like cross entropy loss, right? But then they slowly increase the weighting of the dice loss, as your model learns more and more, right? And the idea is just to sort of optimize the final score function that you're gonna evaluate your model with, right? And so yeah, you just reweigh the loss with some scheduler, and lots of the time you just linearly increase the weighting of the dice score. Right, and now let's talk about some applications of image segmentation. A very common one in the medical field is actually a very basic one is retinal vessel segmentation. Right, so it's exactly what it sounds like. Given an image of, let's say, the retina, you want to be able to segment out the vessels of the image. Right, and a lot of people apply before these neural networks. They applied these different methods. Right, however, after like UNets came out. They just, you just pass this image through a unit and it should recover the final, the retina, the vessels, right? And yeah, there's a very good data set out there called DRIVE, D-R-I-V-E. Yeah, it has, I'd say, around 40 of these images of the retina vessels. That's not a lot of images actually. However, what lots of people do oftentimes is they just crop random patches of the image and then feed that through the model, right? And then another instance of image segmentation is in MRI scans and CT scans. A very common one that's used is brain segmentation, right? To segment all of the different parts of the brain. It might be very useful in like locating tumor. Another one that's sort of not really known, it's more new, is to use these segmentations as a surrogate objective for another task, right? A task might be to estimate the volume of scarring in a heart, right? And what I mean by that is if you take a look at this MRI image of the heart, you can see that beside the endocardium, which is this very bright region in the middle, you have this sort of bright region that sort of looks like it doesn't belong to the middle, right? And we call that a scar. Turns out you could use scarring to help diagnose this disease called HCM. Right? And the idea is here, you want to segment out which pixel belongs to the star. And then from that, you should be able to extract the total volume of the star after you segment all of the slices of the MRI image, right? And so this is a surrogate objective. You're training a model to segment out the star, and then using the segmentation mask, you're able to estimate the volume, right? And so yeah, that's another region where area where segmentation might be useful. You might not directly use the segmentation mask, to gain insights from it, but you could use it from some downstream task later on. And the most common one, obviously, that we probably all know of is street view segmentation. This is very useful for self-driving cars because now you're able to sort of know exactly where every single class object is, right? And that's very important, obviously, in self-driving cars. Last week we talked about this thing called RCNNs. Turns out you can also apply a segmentation branch to it, right? So above we have pretty much exactly what we had last week in the faster RCNN. However, afterwards you also take those features, you pass it through this fully convolutional neural network to segment out each pixel now, right? So now it's like this joint sort of we're doing a bunch of joint tasks, right? We're outputting the bounding boxes, right? The corresponding label of the object inside each of the bounding boxes, and we're also labeling each of the pixels, right? And so that's mass RCN, and it came after all of the papers that we mentioned last week, right? So let's get coding. This week, I've brought some template code for whole heart segmentation on this data set called HVS16. You guys can play around with it and get familiar with the code base. The thing about segmentation is it's actually quite a bit more complicated than just classification on MNIST and CFAR10. So there's a lot of parts to it, right? But your main file that you're probably most concerned about is this train file. Obviously, you could tell that there's a lot more lines than what we had in the previous week's Google Colab, right? But the good thing is a lot of it is just all of these arguments and features you want to pass in. So it's not too important actually training the model. But yeah, so the models are defined in this folder called models, right? And it's in models.py. And so what we have here is we implemented a few of the UNet architectures, right? We have a ResNet, and we also have a few other type of models, pyramid pooling, and then yeah, we have a bunch of different units. So AlbuNet, what an AlbuNet is they just replace the encoder with a ResNet that we've all seen before, right? And then yeah, that's pretty much all they do. They replace the encoder with a ResNet. And so yeah, these are some implementations of UNets that you can play around with, right? And the data is all given in here, right? So I think this is a pretty good resource to work with. And after training your model, it should look something like this, right? So given this ground truth, compared to what your UNet predicted, it's pretty similar, I'd say, right? So that's pretty cool. And yeah, and here I just have all of the papers I mentioned this week, mainly just the DeepLab family and then the UNet, right? And here's some additional resources if you are interested, right? And so this MIT CISO vision segmentation code base, it's actually very good. It was actually what this sort of repository that I had was sort of based off of, right? So if you're not very interested in medical image segmentation, you could just play around with this repository. They use a bunch of different data sets and natural images that are not just black and white images from MRI scans, for example, right? So this is another good repository that they also implement a bunch of different segmentation models. We only talked about the basic ones like DeepLab and also UNet. However, there's a bunch of other ones out there, right? And so, yeah, that's pretty much it. If you're ever interested in other segmentation models out here, here's another good repository. They just basically implement a bunch of the segmentation models because it's not kind of just given to you in the default PyTorch library. So you have to go onto GitHub or somewhere to find it. But the good thing is that you have these libraries out there that make it very easy to implement these models, which is very cool. And yeah, I think that will be all for this week. Just looking at the schedule, next week we will be talking about generative models, right? So look forward to that. A lot of my interests are actually in generative models, so it should be a very interesting talk. And yeah, that should be 2 weeks from now, so November 16th. So until then, see you guys.